Okay, so welcome back. Last time we started to develop uh, our basic derivative rules to kind of speed up the derivative process. So the first thing we had is that anytime we take the derivative of a constant, that derivative is 0. And then the big one for us is this power rule. It says if you have something raised to a power, if you have something raised to the power, when you take the derivative of it, whether you're writing it as d dx or as we often do, we write as f prime, right? You take the exponent, multiply it out front, and then decrease the exponent by 1. So in the case of x squared, we bring the 2 out front and then decrease that exponent, and that's how we get 2x. Or in case of x cubed, we bring the exponent 3 out front, decrease it, and we get our answer 3x squared. And this works whether we're dealing with nice whole number powers like 2 or 3, or whether we're doing negative powers, like our third example here. Right, we bring the minus 1 out front, decrease it by 1, gives us an x to the negative second, which we clean up, and we get as negative 1 over x squared. Or whether we're dealing with fractional exponents, right, x to the 1/2, we bring that 1/2 out front, decrease it by 1, that would get us to x to the negative 1/2. So now, because that has a negative exponent, that whole expression goes to the bottom. The 2, of course, is already down there in the bottom. So we have 1/2 x to the 1/2, and that's actually okay to write it that way. Though a lot of times, especially your book, and you'll definitely see me write it, the 1/2 x to the 1/2 as 2 square root of 1 over 2 square root of x. Okay, and then we saw the same thing with these two examples here, right? Here we brought the 4 out, dropped the exponent by 1. In the end, we get 60x to the third. Or in this example here, we brought the 1/3 down, and it goes with the 10 to make 10/3. And then we drop the exponent by 1, we have x to the negative 2/3. So that negative 2/3 drops to the bottom fraction. So we get our final answer 10 over 3x to the 2/3. Now you could write that x to the 2/3 if you wanted as cube root of x squared, or just leave it as x to the 2/3. Either way is fine. What we were making use of here in that example up above was this rule that allows us to take a radical and transform it into a fractional exponent. Okay, so that's where we'd finished up last time. And so today we're going to continue with these rules, adding another one to our list, which is the sum and difference rules for derivatives. So we say here, let f and g be differentiable functions. Again, remember, differentiable just means it has a derivative. So let f and g be differentiable functions. Then it turns out the derivative with respect to x of f of x plus or minus, because it could be an addition or a subtraction problem between the two functions, that the derivative of f plus or minus g is quite simply the derivative of f plus or minus the derivative of g. In other words, the derivative process distributes across addition and subtraction. So what this means for us is this idea, coupled with our other roles, our constant multiple role, our power role, and our constant role, is that now if we're just dealing with the derivative of any kind of polynomial, then we can just basically take that derivative process through to each piece. Just take that derivative process through to each piece. So for example, we had a function like f of x equals 9x cubed plus 7x squared plus 13x minus 20. Right? We had perhaps this function right here. Then to take the derivative of this, right, f prime would simply be the derivative of all that stuff. 9x cubed plus 7x squared plus 13x minus 20. Then the derivative, our rule up above, says it distributes across addition and subtraction. And our constant multiple rule said, hey, we can pull those constants out of the derivative. So we could rewrite this as 9 times the derivative of x cubed plus 7 times the derivative of x squared plus 13 times the derivative of x minus the derivative of 20. Now I've written this step out this time just because I want to make things clear as we're doing these problems, how everything's coming together. In practice, usually though, we'll just go ahead and do those derivatives since they're pretty easy to do using our power rule. Pretty easy to do using our power rule. So this would be probably again writing out more detail than we have to, but I'd like to be clear. 3x squared, drop it by 1, plus 7 times the derivative of x squared, which would be 2, drop it by 1 would be x. And then here we're dealing with just an x. And derivative of that is just 1. So that would be 13 times 1. And derivative of 20 is a constant, so that would be 0. And then we just clean that up. And we get 27x squared plus 14x plus 13 and minus 0, which would just be still just 13. And so now we have computed our derivative. And again, in practice, if we were to do this, a lot of times some of these steps that I've written out here, we would just skip ahead and do those, without writing out all the detail. Okay. And so pretty straightforward as far as doing the derivative of something that now is an addition or a subtraction problem.